In a lot of situations, when making a choice, we tend to look at quantitative data and compare, some meaningful data to know which one is a better option, which one's a better path, which one's a better situation for our, circumstance, things like that. In mathematics, one way we can compare data is using ratio, rates, and proportions. A ratio is just a number comparing two things that are the same unit. This gives us a number that relates typically some physical feature of the two similar items. For instance, like gear teeth. If a gear has 80 teeth and another gear has 40 teeth, then we have a ratio of 80 to 40, or if you reduce that, it would be 2 to 1. For these ratios here, I'm just going to write them as a ratio. The most important thing to note is that ratios are actually unitless. The units should always cancel. So 30 feet to 60 feet, that's just going to be 30 feet to 60 feet. Of course, the feet cancel because they're right over each other. And we have 30 to 60. Now you can write this as a ratio like that using the colon notation. In mathematics, we tend to write it as a fraction because that way we can actually use it in many different forms. Now we can also reduce this. That's typically what we do. We can divide top and bottom by 30, and you see we have a ratio of 1/2 or 1 to 2. 45 miles per hour to 25 miles per hour, well, you can just write it over each other like that. You see that they cancel. We can divide by 5 on top and bottom. That gives us 9/5. It's a ratio of 9 to 5. Now, what's important to note here is that all of these ratios can be flipped. 30 to 60, 30 feet to 60 feet is kind of the same thing as 60 feet to 30 feet. We typically write it in a certain way depending on context. Maybe you want to know what a bigger gear to lower gear ratio is, what a longer cord to a shorter cord ratio is, a faster car to a slower car ratio. But you could also want it vice versa. So just keep in mind that you can flip these around, right? I could write this as 25 to 45, and then that would be 5 to 9. They're kind of the same thing, but context will tell you which way to write it. 6 minutes to 16 minutes. Those, of course, cancel. We can divide by 2 on top and bottom, and we get 3 to 8. And, of course, $300 to $450. Those cancel. We can divide top and bottom by 150. And that gives us 2 to 3. All right, a rate is different from a ratio in that a rate still has units. It's typically some quantity per unit of time, some quantity per dollar amount, things like that. In this case, 48 gallons in 14 minutes. This is like the rate at which a tank drains with a certain opening and everything like that. So 48 gallons in 14 minutes. This we always reduce. I can reduce by, I think, just 2. It gives us 24 gallons in 7 minutes. Okay, $4.24 for 36 potatoes. This one we can't really reduce because $4.24 has a decimal in it. We can't divide this by 2 twice, and we end up getting $1.06 for 9 potatoes. And this is a little bit simpler, but because there's a decimal in there, you should just be able to just divide it out. We'll talk about that in a unit rate, but this is just a type of a regular rate. 72 correct answers. I'll do correct answers to 96 questions. This is, of course, the rate at which a student got answers correct for a test, for instance. We can divide this by 2. That gives us 36 over 48. divided by 2 again. That's all I did in the first place. And we get 18 correct answers to 24 questions. Make sure I'm doing this right. Yep, we can divide by 2 again. That gives us 9 to 12. And here we can divide by 3. 9 to 12 divided by 3 gives us 3 fourths. So you can directly see that this is 75%. 3/4 is 3/4, so 75%. Correct. All right. The unit rate is different from a rate in that the unit rate, we always divide out the bottom. The bottom should always be 1 in this case. So we get just a single number and no longer a fraction. So let me get a little bit more room down here. 1,500 meters in 6 seconds. This we divide out 6 from top and bottom. And that gives us 250 meters in 1 second, or we could just say 250 meters per second. That's typically what we want. We want some singular unit that defines the rate. No fractions that are involved. That's what we want. Sometimes you can get decimals with this, but that's just part of the idea of a unit rate. It's easier to work with a number than a fraction. I think that's the point. 192 miles in 6 gallons. This is miles per gallon for like the MPG for a car. 192 divided by 6 gives us 32. So we get 32 miles per gallon. 5 cars for 20 people. Using your calculator, you're going to get 0.25 cars per person. So see, I've changed the word from people to person because we only have 1 in the denominator, so it's going to be per person. So each person gets 1/4 of a car. That's kind of a weird one. I don't think you could see that really in real life. $36 for 4 pounds. So what's the dollars per 1 pound? Well, we just divide 36 by 4. It gives us $9 per pound. I should just say pound. That is the dollar rate for a single pound rather than just for 4 pounds. Okay, let's use this information and go on to proportions. A proportion is a way of comparing 2 ratios or rates. So to write a proportion, it's quite simple. We write it like for this one, 48 is to 32. So 48 is to 32 as 3 is to 2. Now there is technically another way of writing this. We could say 48 is to 32 as 3 is to 2. What I'm doing differently here is I'm using these two as a set and I'm comparing them in the same fraction, or I'm taking them and I'm comparing them along the same side of the fraction, so the same numerators, for instance. That's kind of the big thing to note here, is that the numbers that are comparable, they either need to go into the same fraction as I wrote in the first one, or they need to go into the same side of the denominator, so the numerator or the denominator. Now, which way should you do it? I'll show you that with the next problem. That I think there's one way that you should specifically do it. When you have just numbers, though, it becomes a little bit more confusing. That's why I think I tend to always stick with this first way here whenever I have just numbers. I think that's the easiest to think about. This second method is kind of more confusing. But either way, what you're going to see is you're going to have a true statement. because I can divide. Let me clean this up here a little bit. I can divide 48 and 32 by 16, and I get 3 over 2. For the second one, I can divide top and bottom by 3. And on this one, I can divide top and bottom by 2. And this gives me 48 divided by 3 is 16 over 1. And 32 divided by 2 is 16. 2 divided by 2 is 1. And I get a true statement in both cases. So they both work. Now, if I have 6 adults is to 10 children, as 18 adults is to 30 children, what I'm going to suggest to you is to always have a ratio equals a ratio. And a ratio has the units cancel, meaning the units are together. So 6 adults is to 10 children, as 18 adults is to 30 children. What you see here is that now the units cancel. Adults, adults, children, children. And we have just the numbers now. 6 to 18 equals 10 to 30. This is, I think, going to give you the best success when doing these in kind of like word problems, because the mathematics should always work out nicely. There are some cases where if you write it in a different form, it's going to give you different answers. But if you do it this way, it should always come out to be the right way. And you can see that this is correct because I can divide top and bottom by 6. Divide top and bottom by 10 here. And I get 1/3 equals 1/3, and which is a true statement. So we know we've set it up correctly. All right, 12 pens cost $4. So in this case, I could write it as 12 pens cost $4 equals 33 pens cost $11, and this would be correct. The problem is that when you're doing a word problem, it's not written out in this form. You want to have a method that you can always turn to. And so I suggest writing 12 pens is to 33 pens as $4 is to $11. Oops, did I do this correctly? Yeah, 12 pens goes to $4. 12 pens goes to $4, as 33 pens goes to $11. And I can show you that they are the same thing altogether by, let me just cancel those dollars here, by taking the dollar amount here, the 4 over 11, and multiplying by 3. 4 times 3 is 12. 11 times 3 is 33. And 12 over 33 equals 12 over 33. So we have a true proportion there. Okay, let's move on to true or false. In this case, we're asking, is this proportion actually a real proportion? And the way you do that is by either simplifying the fractions to be the same amount. You can also divide them using a calculator to make sure you get the exact same decimal. You can also multiply both sides to get the same thing. I'll show you the last method here because I think it works out nicely. We can't simplify 2/3 and 7/16. They are already simplified. However, I can make them have common denominators by multiplying by the other denominator. So I multiplied by 16 because the other denominator was 16, so I multiplied 3 by 16, and vice versa. 16 times 2 is 32. 16 times 3 is 48. So I should actually have a question mark above all of these because we don't know if they're true or not. We're trying to figure that out. 7 times 3 is 21. 16 times 3 is 48. Does 32 over 48 equal 21 over 48? No. So this is a false proportion. It's actually pretty useless because it doesn't even tell us anything true. So there's really no reason to use that. All right, 48 acres to 144 bags of seed. Does this equal 5 acres to 15 bags of seed? Well, here I can reduce everything. I can, you can see 48 and 144 can be reduced, and 5 over 15 can be reduced. I'm going to reduce this side by 5 on top and bottom. And I believe 144 can be divided evenly by 48. Let me try that out. Yeah, it can. So I'm going to divide top and bottom. I should write it differently here. Divide top and bottom by 48. So 48 divided by 48 is 1. I can say 1 acre. 144 divided by 48 is 3 bags of seed. BS. Bags of seed. 5 acres divided by 5 is 1 acre. 15 bags of seed divided by 5 is 3 bags of seed. And here you see that we have the exact same numbers. So this is true, meaning that you can use this thing here and these two proportions to relate each other, depending on whatever circumstance, right? This looks like a type of farming proportion. So let's say, like as a general rule of thumb, 5 acres to 15 bags of seed is what you want to do for a certain vegetable or whatever you're growing. Then can we scale that up to however many acres? Say 48 acres. Well, then 144 bags of seed is how much you would use. It's the same ratio. In this case, it's actually a rate, not a ratio, because the units do not cancel. Okay, last one. 12 over 28. I can reduce these things. It looks like I can reduce 12 over 28 by 4. Biggest thing I can see. The second one is 6. Yeah. 12 over 28 becomes 3 over 7. Yep. 18 over 6 is 3. And 42 divided by 6 is 7. This is the same thing. So we have a true proportion there. The nice things about proportions is that you can use them to find out new information. So for instance, if 28 tapered pins can be machined from a steel rod that is 12 feet long, then how many could we get from a 9-foot steel rod? Well, we can set up a proportion to find this. So we know 28 pins goes to 12 feet. Now we're asking how many pins goes to 9 feet. The way we set this up is first off finding the proportion. And instead of writing a question mark, I'm going to use the letter X. This is called a variable. It's what we use to find out unknown values of numbers. We know the number, there is a number there. We just don't know what it is. And we're going to use mathematics to solve for that variable. The way we do that for proportions is quite simple. The first step, though, is to make a proportion. So I recommend you always write ratio equal ratio. In other words, the same units over each other equals other units over each other. We know 28 pins goes to 12 feet and X pins goes to 9 feet. 28 pins over X pins equals 12 feet over 9 feet. Pins goes to 12 feet. X pins goes to 9 feet. This is always how it's going to work. There is one special case, which we'll talk about in another video, called a inverse variation. which it doesn't work quite the same way. But for most of the proportion that you're going to see, it's going to work out this way. Make sure the things that are related to each other are on the same side of the fraction. To solve this proportion, now that it's set up correctly, we have a ratio over ratio. You can see this because all the units cancel. We do what's called cross multiplication and then division. In other words, multiply like across the denominators, or across the fractions, I should say. 28 times 9 equals x times 12. I'm going to write it like this way. We always write the variable after a number when they're multiplying, so I'm going to write it as 12 times x. Now, 28 times 9 is 252. So cross multiplication is the first step. The next step is division. Whatever you're multiplying x by, you divide it to the other side. So x will equal 252 divided by 12. In other words, 21, and we know x is in pence because that's what we wrote it as. So x equals 21 pence. So the way we solve this is cross multiplication and then division. Cross multiplication and then division. Go across the numerator and the denominator and multiply everything. That's what cross multiplication means. And then whatever you're multiplying by x by, you divide by it to the other side. In other words, take this number and divide it by, let me do it this way, by that number. That's always the process. A photographer must mix a chemical in a ratio of 1 part to 7 parts. 1 part chemical, 7 parts water. How many ounces of chemical should be used to make 3-quart total mixture? So we're going to want to create a proportion here. That's how we're going to solve this. But there's some preliminary work we have to do before we can even do that. What's important to note here is that we want to know how many ounces of chemical need to be used. We also know that we have a 3-quart total mixture. The problem here is that we want to know what ounces are of the chemical, and here we have quarts. We don't want the unit quarts. Whatever unit we're going to use in mathematics is the unit we're going to get out, so we want ounces. Well, thankfully they gave us this conversion ratio. 1 quart equals 32 ounces. So if we have 3 quarts, so 3 quarts then would equal, if 1 quart is 32, then 3 quarts is going to be 3 times 32, or 96 ounces. So how many ounces of a chemical should be used to make a 96 ounce total mixture? How many ounces of chemical? Just so you know, that's what we're looking for. So this is going to be our x. X ounces of chemical goes to 96 ounces of total mixture. So we have one side of the fractions. X ounces chemical goes to 96 ounces mixture. What's the other side of the fraction? Well, that's going to be this 1 part chemical for every 7 parts of water. Now, if you don't know 1 part to 7 parts, this is a convenient way of writing a relationship whenever you're doing kind of mixtures. The word part can be changed for any unit you want. 1 gallon chemical for every 7 gallons of water. 1 bathtub of chemical for every 7 bathtubs of water. 1 ocean of chemical for every 7 oceans of water. It's just a way of comparing two things that can scale to whatever needs you might have. In this case, we want ounces, right? That's what we're looking for. So I'm going to change this to ounces. 1 ounce chemical for every 7 ounces of water. So to write again what we have here, we have X ounces chemical goes to 96 ounces mixture. And what I have in this part here is 1 ounce chemical goes to 7 ounces water. Now, do you see a problem here? The problem is these are not the same thing. We need to have 7 ounces or some number of ounces of mixture, not of water, because that's the mixture was given for the first, right? This is all given to be mixture, so we have to have mixture there. Mixture is just a a mixture of chemical and water. So if 1 ounce of chemical and 7 ounces of water are being used to make a mixture, then how much mixture is that making? 1 ounce of chemical plus 7 ounces of water gives us chemical plus 7 ounce water gives us 8 ounces of the mixture. So instead of using 7 ounces of water, we're going to use 8 ounces of mixture. And now you see we have the same units here, we have the same units here, which means we can use ratios and solve this thing out. X ounces chemical to 1 ounce chemical equals 96 ounces mixture. I'm just going to use M to 8 ounces mixture. And you see the units cancel, which is good. And you can also see that X goes to 96 as 1 goes to 8. So we have everything lined up correctly. Now we can use the cross multiply and divide process. X times 8, 1 times 96. X times 8 is 8x. Let me do it like this. 1 times 96. Again, we have 8x equals 1 times 96 is just 96. And then we divide. Cross multiply, that's what the blue and the green gave us. And then divide. That's going to give us x equal whatever 96 over 8 is, which is 12. So to get a 96 ounce final solution, or total mixture, I should say, we need to have 12 ounces of chemical, which means, just a side note, 96 minus 12 gives us 84 ounces of water is also required for this total mixture. We got to figure out how much mortar mix a mason needs. 640 blocks, 12 bags are required for every 100 blocks. Of course, he cannot buy a part of a bag, so if we have a decimal in the end, we're just going to have to round up. That's all that means. How many bags will he need? That's what I was looking for. How many bags? Well, we're trying to figure out what is the number of bags, and so that number is going to be x. So in other words, x number of bags goes to, I don't know why I wrote that, goes to 640 blocks, because we're trying to figure out how many bags for 640 blocks. And we know that the guidelines suggest 12 bags are required for every 100 blocks. We have 12 number of bags goes to 100 blocks. And you can see we have the same units on both sides. So now we can set up a proportion to solve this. X over 12, because the units will cancel, equals 640 over 100. Cross multiply and divide. X times 100 is just going to be 100x. And 12 times 640, that gives us 40, gives us 7,680. That's the cross multiplication. The last step is division. I'll do that in red here. think it's a little bit easier to see. So all we have to do is take 7680 divided by 100, which gives us 76.80. This is going to be the number of bags, right? Now, since he cannot buy a part of a bag, or in other words, 0.8 of a bag, that means that he must buy 77 bags for the job that's he's currently doing. Okay, last application problem. Here we have standing trim requires 0.8 to 1.0 hours of labor for 100 linear feet, and standing trim requires 0.5 to 0.75 hours per 100 linear feet. What's the minimum and maximum number of total hours required for 360 linear feet? So if we're going to look at the maximum and minimum, let's actually figure out what the max and mins are. We have 0.80 to 1.00 hours and 0.50 to 0.75 hours. And these are both for 100 linear feet. So if 0.8, looking at the minimums, right? If 0.8 hours for 100 linear feet and 0.5 hours for 100 linear feet, then we have 1.30 hours per 100 linear feet as a total. And the maximum would be 1.0 hours of labor per 100 linear feet and 0.75 hours of labor per 100 linear feet. Then we have 1.75 hours of labor per 100 linear feet. That's the maximum and minimum for this kind of situation. Now this is for 100 linear feet, and we're looking for 360 linear feet. So we write a proportion. As we're looking at the max and min, we're going to take this in parts. We're going to look at the first part, the minimum here. 1.30 goes to, this is say hours, goes to 100 linear feet. I'll just write feet there. Goes to X hours for 360 linear feet. This is a proportion. Equals 100 over 360. Of course, the units cancel, right? We have hours over hours on the right, those cancel, and we have feet over feet. The way I've written it here, the units will always cancel. That's why I've written it this specific way. Now we can cross multiply and divide. 1.3 times 360, x times 100. This is going to equal x times 100 is just 100x. 1.3 times 360 is 468. Let me do it in blue here. And we have 100x still. That's the cross multiplication. Now we divide. Always by the number that's in front of x. So x equals 4.68, and x is in hours. So this right here is going to be the minimum number of hours required. What's the maximum? Well, the maximum is 1.75. So we're going to use the exact same ratio, or I should say pretty much the exact same proportions, except now instead of 1.3, we're going to use 1.75. This one I should just say is a minimum. Okay, now we can do 1.75. These are hours over x hours equals 100 feet over 360 feet. Cross multiply and divide. 1.75 times 360 equals 100x. Just write that again. 1.75 times 360 is 630. That's the cross multiplication. Now we can divide by the number in front of x, which is 100. And we get x equal to 6.30 hours as a maximum, which means it's going to take 4.68 hours, or 4.68 to 6.3 hours per 360 linear feet.